People. Good morning. This is the second lecture in this module on physical metallurgy, polymer deformation, heat treatment, and surface finishing. Last time we talked in quite a bit of details about how you take a piece of metal and what happens into that piece of metal when you pull on it. So first you stretch the bonds, and that's the elastic behavior, and then you get into plasticity. And I think I got a little and I got some momentum going, so I talked a lot about grains and dislocations into the metals. Hopefully some of it was understandable. I didn't have too many questions. I tend to get more questions on the applications than the theory, but it is part of my goals to have you understand quite a bit of fundamentals. I'm originally from Quebec, Canada, so the teaching style is not like in Europe where I'll be drawing equations all day. But it's not as focused on application. That's what you'll see in general in my module, where I try to bring both together. And you can ask the question on whatever you like. There's no problem there. So forming of metals is something that we're going to wrap up. So we talked about what happens when you deform it. Then I mentioned that you try to do it hot if your purpose is to homogenize the material. So at this point, that's pretty covered, and I'm holding to my promise to go into a relatively similar level of detail with plastics. So it's a material class. We're not going to talk really about ceramics. I know about ceramics. They will have some of the same behavior. You can have a ceramic that's going to plastically deform with dislocations in it, but it's at high temperature. Most ceramics at ambient temperature don't really get a lot of plasticity in them. They get a little bit still, but very little. So after we talk about how the plastics deform, we're going to talk about forming them a little bit the same way as we did with metals. And that should wrap up about the portion about getting into a shape already. So we're going into a relatively accelerated mode, talking about taking a piece and making a part out of it is what we're doing right now. So this is probably something you'll remember, that steel is hot when you make it into shape at high temperature and you're trying to homogenize it. We talked about the grains that will build up dislocation and then eventually recrystallize and grow if you keep them for an extended period of time. So there's a lot of diffusion, and that's how you can refine and homogenize your microstructure. One thing that I did not talk about is the energy associated with deforming that metal. Even though it's hot and it's red, it still requires a lot of energy to get into shape. Now, if you put work into the metal, by law of conservation, if at the end of the day in the microstructure, you don't really change it other than refine the grains and getting into this steady thing. So everything goes into heat. And therefore, if you go to a rolling mill, which would be a little bit hard to do these days, they don't continue having to heat the steel when it comes out of the furnace. It goes from one roller to the other, and the speed at which the process of taking the big ingot and making plates out of it is at a speed so you keep up with your temperature of that steel. And sometimes you even have cooling system on some of the rollers. Not all of them. It depends what you're doing. But it's just something to keep in mind. And to that extent, in the industry, so I don't think around campus, or when you go to the general population and somebody says, oh, there may be a hot spot, they mean something on the piece of metal that you're making. But in the hardware, structural material arena, in these mills, when you make the steel, if you have condensation or if there's something that's all the sun is leaking in a cooling system and it gets on the product, it's going to quench that surface. So you have a big, big factory and everything is red hot, and then in one spot something's dripping from the roof or whatever it is, and that will quench that area. And we're going to talk about heat treatment in other portion, but it's so. I mentioned about pipelines. I said it was going to be a topic for the semester. So on pipelines, they have those, and it's a problem in terms of the resistance to stress corrosion, cracking, and other issue. I mean, it's essentially local brittleness because you quench and made this a little bit more. It's not like glass, but it's a lower toughness material in that zone, and that comes from the mill. And again, just specifically because everything is hot, except for what could come off the roof, could come out of a cooling system, just condensation. So it's unfortunate, but it's part of the reality. The little diagram here just shows a little bit the contact force as you go through the process of forming. I don't think there's a whole lot of relevance other than, as you can see, the dashed area is force over distance, so that's energy, and that's the energy it takes for taking the bar from one side to the other, and that's what creates the heat. So let's go to the next. We mentioned about deforming at high strain. Hundreds of percent for going for this shape all the way to something a lot thinner. Could be 1,000% strain. So, a factor of 50 reduction from the original thickness to the final thickness. It's done at high temperature and high strain rate, and part of this is, again, just to keep the metal temperature to the desired range, so you produce enough heat to go where you want to go. If you work on a prototyping project and you have the option between hot rolled and cold roll for a piece of metal, the big difference when you do things cold is you don't have that cooling effect of being hot going to ambient temperature that causes distortion on parts. So when you have something that's cold worked, it has better tolerances in how flat it is and how mostly the flatness. You have a much better dimensional control. It's going to be typically a higher yield strength and less elongation at break. They kind of go together here. So you build up essentially a microstructure that's got a lot of dislocation and small grains in it. There's a lot of situation where you do want to do that. So if you're thinking about a copper wire for electrical conduction, if it's really hanging between two big electrical poles, you don't want it to just deform and sag over time. So you do want some strength into it. So it is cold drawn. So in this case, it really is to increase the yield strength. It's the same for certain aluminum alloys that don't go through a heat treatment. So if you have the body of a boat, high performance boat, a sailboat that's out of aluminum, a lot of time it's been deformed to a good extent. So it's cold formed to raise the yield strength, which means when you weld it or when you do other things to it, that goes away. You can anneal that cold form product. So at that point, you get both. You get it to be straight, and that annealing is done at relatively low temperature. And the big advantage there is if you machine something that's already annealed, there is no residual stresses in it that's going to cause distortion. So it's just very important. And we'll talk a little bit more about machining as far as how we make parts later. Okay, well, there are a lot of other ways. So we don't have a ton of time, but let's spend just a little bit talking. You've heard about extrusion, so extrusions. Not sure why it's doing this to me today. Oh boy. Which one is this? Well, I'm sorry about this. There's a slideshow. Quit. I have to duplicate the screens. Okay, so what we're going to do is really talk about how we, the different ways, and you see it on the screen, on how to form the metals. The most important thing is you have a lot of options, and it really depends what you're trying to do in terms of shape. So the extrusion is the case of trying to make something very long. The loads that you apply are compression, so you're not really limited in shape. You really get it through a die and inform the shape. It's used a lot for aluminum because with aluminum you can make tool steel dies and process it through it. When you get to steel, it's a lot harder. It just requires a lot of energy and the kind of tooling, and not just for strength, but for the toughness it takes so things don't break, makes it very difficult. So that's why we talk a lot about aluminum extrusions. Deep drawing is also used for aluminum a lot to make the Coca-Cola or Pepsi cans. So here you start with a flat. It's the upper right, and as you deform it, you need a lot of work hardening into that aluminum, so the edges here don't thin down and break. So it's a little bit the same effect in the last class when we talked about necking in tension. You do have tension going on there. So the type of aluminum that you need to make a soda can is very, very specific, and even in terms of the orientation of the grains that allow you to get sufficient work hardening so you lose your thickness in some of the areas. And what they do to be able to recycle the aluminum, that's interesting, is they'll have a different chemistry for the body of the can and then for the little opener that's on top. So when you remelt everything together, you still have a chemistry that you can use again. They don't mind as much the chemistry of the little opening tool, so it actually has a lot different chemistry. If you see this process, that's why the bottom of the can is a lot thicker. It's not so much because you need it to be thicker, but it just in the process, you really get thinned down on the edges. Stretch forming, we'll talk about that in the next slide. It looks like it won't be that useful, but it's used quite a bit in aerospace. For bending, what I thought I'll do is, because it looks so simple, if you look at a product that's, let's say it's a box for something important, a safe or something like that. The way you do it, let's say you start with a flat piece, and then you'll have, let's say, your sides here. So let's say I got a side there, I got another one there, and I'm repeating it here. So I could go cut out from a plate something like this, and then I come and I bent those edges. But this actually, as far as not only prototyping, but making parts, is something useful to keep in mind. Is why would I do that if what I can do is also say, well, here, I'm going to make this way. So later, I can bend this over this one and make a strong corner. And now my welding is not going to be right at the corner. It's going to be protected. I'm getting a lap. So you do it here, you say, okay, I'm doing the same here. And you can get very creative in the shape of something like this, and it's totally doable. So to make a safe out of even relatively thick-walled metal, you can get into a shape where there's going to be even, like, if you can put away the openings for where you're going to want to put mechanical systems. So that gets prepared and then goes to the forming press, and everything gets bent and put into shape. So very effective, and you're not, the welding of this doesn't matter anymore. It could just be even spot welding, so not along the whole length. So it's really easy to do. And then just like with car bodies and other things, what you do is you put some compound and hide all of this, and you can't tell there was anything in there, but it's how you made it effectively. Okay, so in aircraft fuselage, it is very important, the shape, the external shape of the aircraft. They spend a lot of time in aerodynamic, doing computer simulation that may or may not work, and then they go in flight and make some measurements, make some adjustments. When they decided that's what they want, that's what you need to build as the engineers. So let's say that I'm trying to do that. I'm trying to get to a very specific shape with a really high quality piece of aluminum. Well, I bend it, I got some elastic behavior, so maybe I'll bend it twice what I need the shape to be, and it's going to come back about where I want it to be. So the idea here, when you clamp it on the left and you draw it so you get it on that stretch shape, is you have plasticity to the entire wall of the sheet, and that means everything is deforming. It's going to conform with the shape. When you let it go, nothing happens, because you're not just deforming the outside plastically or the inside, so it's not a tension compression that's going to try to come back on you. Everything is in tension, and when you let it go, nothing happens. Another big advantage for doing this is in the aluminum alloy, in the way you can make the sheet is low strength, so you can form it more easily. It's got more work hardening. And just deforming, so generating a lot of dislocation and deforming the grain and the material, actuate a hardening process that is a dispersion or precipitation hardening. And we'll talk about that in details. But it's a great coincidence, because first you get the shape that you want. You don't need the same amount of forces. You can do it without having a risk of forming a neck or a thin zone. And then that actuate the heat treatment process to raise the properties after the fact. And the same apply to rivets. So you have a rivet. They'll keep it a lot of times in a freezer, so you don't get the transformation to start. And then it gets fed into the riveting machine, hammered, and just after that, within about 24 hours, your yield strength goes up 50, 80%. So it could be more, but the idea there is you have the ability to form without causing pre-cracking or any issue really with the aluminum. It's soft, and then all of a sudden it gets into shape at ambient temperature. So so when you make a discovery, the people that realize that this has this effect, they probably didn't know exactly what it would be used for, but there are special applications for this process. Forging. I want to mention it because it's still used quite a bit for tools that need to be strong and have a high toughness as well. So you get to your final shape by deforming typically hot pieces of metals, and it's not always hot. So if you look at a bolt, the way you do a lot of boat heads is you start with just a rod, and then you cold form that shape that's going to, let's say it's an hexagonal head that you end up with. So you want to make a fastener that really is kind of bulky and useful. So let's say I got my hexagonal head here and I got the shaft. So the process of making that head, bang, cold form. Reasons, well, you save money if you don't have to heat it up, if you have enough forces to do that. Now, you do it by steps. It's not just a one-step process. But the idea there is you're going to have so much material in this zone that even if some of the behavior in terms of ductility, now you have a gradient in properties, but everything is higher strength. Because if I look at that fastener from the side, the way it looks like is I have the head here, then I have a shank. Eventually, maybe I get to some treads. And then there's going to be a knot on it. So the weak portion, a lot of time, is the treaded zone. It has very big stress risers. So there is no need for this to be perfect. Strength, especially the fatigue strength, is going to be limited by this portion. So it's a money decision. It's done cold. Questions? All right. So what I'll say there in terms of forging is you are able to form a little bit of a skin because you do have friction between the die that you're using and the component, and that friction essentially plows the material, so you form a forging texture that gives you better properties than if you took the part and machined it. Does that work always? No. Sometimes you can have a lap defect during the forging, so a surface that folds against another, and then all of a sudden you reduce the properties. So a lot of times it's better. There are cases if you don't control the process where you can introduce anomalies near the surface. And therefore it's not used a lot in aerospace. It will be used in automotive when you use steel and you say, oh, I need this really to not break, so I'm not going to try to cast it. At the same time, I don't want to have the expense of machining it all. So your steel wheel is going to essentially be forged because casting is not good enough, and machining a wheel would be extremely expensive. Now, we're not limited. So when I showed you this previous slide with the big piece of metal right in the center, and then you're trying to form it, the same way that when we talked about casting earlier, you can have inserts to make complex shape. You can do that in forging as well. So you can make shapes that are not just two pieces coming together, that have side protrusion or depression, holes. You can make fittings, essentially, that are forged so that you're not limited except by the cost of the tool and all the press to make this happen, and the design of that process, because you have to do it one step at a time. And sometimes, a lot of time in forging, you have to stop and re-anneal the parts, so your yield strength goes back down, your ductility goes up, and then you can continue to the next step of forging. Tube forming, so that is done with all materials. One advantage of the drawing process is a very tight dimension tolerance. So the same way when we talked about stretch forming, that you get deformation through the entire thickness, you have the same effect here where everything gets pulled. So there's not going to be a whole lot of spring back when you unload something that's been drawn. So for a lot of complex mechanical systems, In an engine or a really complex gearbox, you will have tubes that are drawn as opposed to just any tube made in any way that you like, just for dimension tolerances. Okay, well, we are going to switch gears and talk about plastics. I have a few examples here for tubes, fittings. There's this big pipe in green to the right. A lot of under the hood components for cars are made out of plastic these days. And two of the very common processes are injection molding. So same way that we've seen it with the die casting for metals. Here you heat up the plastic and you put it into a mold. It's at a much lower temperature. It's very easy to do. There are challenges in terms of mechanical properties, and we'll talk about that. Extrusion is also very common. So again, you heat things up and then you get it through a die. So before we get into how the processes work and what happens to the part as a result, I'll do like I did with the metal, so we'll go a little bit more into details what happens to those plastics when you deform them. A lot of times we can't use unreinforced plastic for structural applications. So this chair, if you sat on it for 20 years, there'll be a problem. I mean, even if you sleep over it, it's not like your load's going up, but you can bend the back. I've seen that. It happens in our office sometimes. Somebody just take a nap and, ooh, problem. So why do we have this? The main reason is we have creep, so we have essentially that plastic behavior, everything moving around in the plastic at ambient temperature, because the melting point of that plastic is not super high. So the one thing to keep in mind about creep is it will happen in most materials when you're above half the melting point of that material, whether it's a polymer or whether it's a metal. But you take the melting point in Kelvin, so in absolute temperature. So if you take a polyethylene that you can start melting at, say, 200 degree centigrade, so that means, let's say, 500 Kelvin, so at 250, even below freezing, you're going to have that creep behavior take place. It's very, very cold, and you can lose it, and some of the plastic do become brittle at low temperature. So there are a lot of analysis done on plastics in terms of their creep behavior that's been really, really focused on pipeline again. So plastic pipes for natural gas distribution in cities. It used to be a lot of steel there, but because it's lower pressure, you have a lot of advantages of putting the plastic on, not just for cost, but how you have to control corrosion over time. But you limit in the pressure that you can put on that pipe long term. So let's take an example. There's a lot of plastic pipes. Let's say they'll take 1,000 psi of pressure before they burst with water. 2,000 is even typical. But they are rated to carry only 100 psi of pressure, so 1/20th of that for long-term service. And that is, let's say that's at ambient temperature. If it's a hot water line, maybe now it's 80, or maybe it's 60, and then all of a sudden you really are getting to your design limit, even if it's only 1/40th of what it'll take to break it short term. So just to show the significance of this, that yeah, the piece of plastic looks great, but the load that I can put on like this versus the load that I can put on for 20 years in 1/50th. So very, very significant. Why? When you do the rapid loading of the plastic, what happens is the same as with metals. You get a little bit of a spring effect between those molecules, the chains of polymer that are in the plastic. It's just stretching of the van der Waals bonds. It's not really the atomic bond that you have in a metal. So it's not as stiff as a metal, but it is an elastic behavior, so it comes back. Over time, the first thing that happens is you think about a polymer chain, and it can be very, very long, but it's going to have some side groups. So I'm just going to draw the carbon, and then, oh, I got another carbon here, and then I keep going. So that carbon has its 3 hydrogen, and it's a resistance. Think about a piece of spaghetti that has something branch to it, and you're trying to slide them together. They won't. They are, to some extent, analog. But over time, what happens is this chain is going to rotate back and forth. So under load, eventually it'll get in a configuration where it's possible to start moving, to slide over a small distance. So that's the first step of viscoelasticity. It doesn't become super important in the deforming we're going to be talking about, but it's the first step that happens. Now, the next step, what people talk viscoplasticity here, is that entire chain, after having done a bunch of rotation, is in space going to start moving from where it is now. So this is kind of shown schematically here. So you start with an idea of where that macromolecule is in space. You can stretch it, and then it's going to kind of move around on small distances, so just stretch along its length, and then eventually it's able to ramp, is a term that's used a lot, and now all of a sudden it's at another place, but it had to overcome other obstacle. When you reach that stage where the shape is not where it used to be, the reason we call it viscoplasticity is if you unload it, there is no big driver at ambient temperature to go back to the original shape. But you would be very surprised because you can deform plastics to a pretty fair amount. And when you heat them up, they will go back to the original shape. So they keep that history of how they move into place. So here, the analogy of the spaghetti, I think is relatively useful. I mean, it helped me a lot in the past. And I'm going pretty fast here on something that I've spent a lot of time on. So if there are questions, you go ahead. But if not, we'll talk about more practical materials. So most plastics that we use, other than polycarbonate, other than the transparent plastics, have crystals in them. So they are semi-crystalline. That's the case of polyethylene, polypropylene, PVC, nylon. There's a long list of plastics that we use that are at a fine scale. When you make them, will have the equivalent of grains, and we call spherulites. And it's shown here on the screen. And these spherulites will be different than the grains that we talked about in casting of metals. So what happens here is polymer is not perfect. So what you use as a feedstock, they'll actually put nucleation agents. So if we look here, we are in the melt. So we at a big pot, let's say we're doing compression molding, that's easy. So we just filled it up, and then we have these very tiny particles that are added on that enable the initiation of crystallization on, let's say, polyethylene, for example. So it starts right here, not on the surface of the mold in this case, and then you start going in certain direction. Now, the big difference there, when you start making those crystals, is not all those chains can get organized. So if you try to take spaghetti and you'll say, oh, I'm going to align some portion here that are going to give me a crystal structure, there are other parts that have the knots in it that stays in between. And that's what you see here in this kind of layered structure where you have the crystal face, that's the crystallites, and then you have the amorphous intercrystallite space. And this has a lot of implication on why we do forming of plastics as well, because we can think of this as a relatively low strength material. The reason I say that is if I think about pulling, so you have a lot of those, right? So if I complete my schematic here, I got one spherulite here, I got one there, and then I fill up my space. And if I go and cut a piece of plastic that's just been cast or molded, that's what I'll see in it after etching. It's low strength because let's say I'm looking at this zone here. I got two crystallite, and then I got the unorganized layer between them. Crystallite is very strong in terms of its yield strength. Now you have to, if you try to deform that crystal, it takes a lot of energy because the dislocation in there is very complex, takes a lot of energy. What's easy to stretch is this amorphous zone between the crystallites. If it wasn't for having crystal in polyethylene, we couldn't use it, even for water bottles, because it's too soft as far as the amorphous portion of it. It's the crystallite that make it strong. So here, if I'm thinking about pulling this way on something that's been compression molded, I'll be able to shear and essentially get my deformation to take place in the softer zone. And therefore I get deformation easily. So that's what happens at the beginning of yielding. So what you see in this schematic is stress and strain over time as you keep pulling into the material. You go from spheres to something elongated. Eventually, all those crystals that we've talked about, they get reoriented, and now you have a composite that is reinforced. Now, you don't have to take my word for it, because to the extent that a plastic bottle is relatively soft, a nylon cord or a polyethylene rope is pretty stiff and strong for the same amount of material because it went through this transformation. So in deforming it, you went from the as-cast structure to something that is fibrillar and very oriented and is essentially almost like a glass reinforced plastic internally, where the crystallite just make that bridge and they do carry the load. You don't have a load path now where you're just going through the amorphous zone. It takes about 500% strain for doing this. So when you take a piece of plastic and you do that pull test that we talked about a lot last class with metals, you'll form the neck. So it'd be a section that's, let's say, half the width and half the thickness, but it's going to be so strong because of this reorientation, it's not going to break. A lot of times it's going to propagate up and down, and then all of a sudden you start with something this long, comes this long before it actually breaks, and your load goes up, your strength goes up by a factor of 3 to 5, let's say, on actual strength of the material. It doesn't show that for the load, because now you have a section that's only, again, 20% of what you started with. So, ropes is one of the main applications of doing this. Extrusion, to some extent, gets you towards that as well. Now, there is one problem with extrusion. I want to emphasize it, which is, let's say you're making a pipe by extrusion. So all your deformation is going this way. So the structure internally aligns, and that pipe is a lot stronger than it is in the hoop stress direction. So unfortunately, when we prepare plastics for making pipes, we don't have the orientation of greatest strength being the orientation and surface that gets the biggest loads. If you remember, tin wall pressure vessels get twice the stress in the hoop direction to expand the diameter than along the length. And here you're pulling it along the lengths. It's just the way it is. So there's nothing to do there, but I guess what I want to emphasize is when you go through this extrusion process, you are still raising the properties quite a bit, because you did succeed in eliminating those ferrulites, the big as-cast structures of the semi-crystalline polymer. Okay, so how it works, it's here as opposed to metal casting. It's very clean, it's low temperature. You heat up pellets that are made from the other process. The first process is polymerization to make that the raw material. But for making parts, you take pieces of that and you heat them up and push them into your mold. So there is a lot of things that happen there. You need exit ports. So you're flowing your polymers, and you're going to have places where you want the excess to go, so you don't have porosity in there, so you don't want to try to fill up the end of something. You wanted that end to be endless, so you put a little extra, and then you cut it off. That's very, very typical for getting good properties. Now, depending on how you cut it off, I'm showing a little, it's this big, a knot that was holding out the pump system, the out pipe for a big boat that broke and sank the boat. So it wasn't a happy ending, and everything. The only thing that happened there is the effect of forming the part by molding. So let's say I have my mold here, and I'm flowing polymer in it. And I got a velocity distribution. It's a little bit like a thin film effect that I have on the surface of the mold that causes everything here near the surface to be oriented parallel to the mold. I'm able to improve my properties, my mechanical properties, significantly through this orientation. But when you cut off something, even if you just sand the surface of this part, now all of a sudden your strength and your cracking resistance goes down significantly because you lost that orientation factor on the surface. So it's an advantage for making parts, and you can see all the flow lines here on the making of these parts. So when anybody looks at this, it can say, oh, it was molded, and there is a mold line going on right here as well. Oh, so there's a risk of cracking. That mold line means that for speed reasons, they didn't have just one place where the resin was being injected. So in this example, you have resin coming from one way, you have resin coming from the other way, and it's going to make what we call the bond line. So over here, it's going to turn like this, going to turn like there, and right here is essentially an interface. So what was coming out from one entry point into the mold and from the other entry point into the mold, and you really would like those mold lines or bond lines to not be in an area of high stress. That's not what they did here, so it cracked. And it started by this piece that was taken off that did not need to be taken off in the exact area of the bond line. So getting all the orientation eliminated, and then of course sometimes it can be over tightened as well. It's not just one factor that leads to the failure sometimes. So just a little bit more on how the heating system and the extrusion work. This is an example that I'll bring to the recitation where it's cracking slowly over time. And the reason I want to emphasize this is we think of plastic as, oh, great, because they don't rust. Okay, they don't rust, but they can still be susceptible to cracking in an environment. And one very specific example is oil or any solvent. So if you use even acetone on a piece of plastic, it will really soften because that acetone diffuses into the polymer and kind of make it liquid all of a sudden, because it's essentially reducing this van der Waals bonds between the different molecules. So it's as if you were melting it. It's useful because we use that solvent cement concept when we have two pieces of plastic, we want to bond them together. You put a little bit of acetone-based product, it melts the surface, and when you put the two pieces together, you make a socket joint, and it's essentially welding, but just done by putting a little bit of paste, putting the two pieces together. Very, very effective. Now, here on a sprinkler pipe about this big, if there is oil in the water system of a specific kind, it will have the same effect of going into the structure, making everything really weak, and all of a sudden you're cracking. So what happens here is, this is a cut view. It's a crack that started. This is the inner diameter. It's going out. You had one crack that started here, one there, plenty of them. And when you see plenty of cracks, it means that the cracking started very early in the life of the part, and all of them grew at almost the same speed. So it's a very, I guess, damaging effect to have that happening. Yeah, extrusion. So I guess that's the negative side of the story here, where there are a lot of things when you form those plastics that are going to have a very strong effect of whether they're going to break or not long-term in creep or fatigue. Just a little notch on that pipe and your properties are going down quite a bit. Just a little bit of oil inside of it, and then all of a sudden you have a problem. And this goes back to one of the team here in terms of processing applications. Just understanding what's going on in the material allows you, I mean, it is possible to prepare a home heating system without putting oil in it. But if you don't tell the people that make the system, oh, they'll use cutting tools, and there'll be a lot of contaminants going into the pipe, and 5 years later, now they realize that they have a big problem. And it's, you know, you could say, I could have thought about it on the first place, but having that history is essentially, if after 10, 15, 20 years of using those pipes and understanding what happens, first of all, long term, that the strength's going to be going down by a factor of 20 to 50. And then is there going to be any interaction, in this case, with the water? And that's where I have another example here of very cool technology where you have plastic on the inside, you have a little aluminum layer, and then you have plastic on the outside. The purpose of the aluminum layer was to prevent oxygen from getting into the heating system, because that causes corrosion of the burner system and everything in there. So it's an oxygen barrier for going inside. And it's also very nice if you try to lay out these pipes under a floor, you're able to bend them and they'll keep the shape. So the plastic would want to bounce back, but because you have an aluminum in there, it's going to keep the shape. Now, in terms of application, one problem is the plumbers really like that types of pipe because they could get it into any shape they like very easily. So they started using it for potable water, which has oxygen, and the plastic was not engineered to resist oxygenated water on the inside. So you had accelerated degradation of the inside, corrosion of the aluminum alloy, and bursting all the way to the outside. and that happens in thousands and thousands of homes. I'm starting to rush here, so I think we'll break and take it from here. I didn't give time for questions, but we can, if you guys have some, we can follow up with that. Thank you.